Hello everyone, I am Íñigo Íncer from UC Berkeley. Today we are discussing the solution of inequalities over general preorders. First, we discuss the notion of a quotient over preorders. Then, we introduce two new algebraic structures that support the expression of closed-form solutions for this quotient. What is the quotient problem? In many theories of computer science and engineering, we are interested in solving expressions of the form ax less than or equal to b. Now, the binary operation is very often monotonic, which means that if x is a solution to our expression and y is less than x, then y is a solution to the problem as well, which means that what we are really interested in is in the biggest x that satisfies the expression. This biggest x is called the quotient. What we provide in our paper is an algebraic structure that supports the closed form expression of these quotients. The quotient is an old problem. Many decades have seen papers and works dedicated to the question, how do you design a component that composed with a known part of the system results in the system having a property of interest, a behavior of interest. The issues that appear when we do such a thing are, how do we model the system and the components? How do we model composition? What does it mean for the system to conform a specification or to refine a set of behaviors? In the logic synthesis community, the form that this problem takes is the following. We want to find a missing circuit that, added to the existing circuit, results in a system having some given property. The specific problems that have been addressed in this line of work are finding quotients for specific topologies, either be circuits connected serially or in feedback or in parallel. The problem is relevant to control systems. In control systems, we wish to find the specifications of a given object, a given controller in our system, such that the resulting implementation of our system has a given specification. The problem is important to communication systems. We have a sender and a receiver, and we wish to find the specification of a translation mechanism between sender and receiver so that the two parties can successfully communicate. Due to so many works in this quotient problem, there was an effort of unification, an effort that used as the underlying objects for the theory languages. Composition was assumed to be either interleaving composition or synchronous composition. It allowed for any topology, and conformance was language containment. The problem was reduced to solving equations ax less than or equal to b, and the largest solution was computed to be that expression. This work addressed the question, what kind of algebraic properties do we need of our binary operators and unary operators if we have them in the theory, so that we can have a closed form expression to the quotient. This approach was based on sets and could not account for more complicated theories like assumed guarantee contracts or interface automata. In our paper, we propose an algebraic structure based on preorders, not on sets, that allows us to compute quotients for all these theories. We introduce two algebraic structures from this point on that will allow us to solve quotients over any preorders. First, some definitions and notation. Let P, comma less than equal be a preorder. We will refer to a preorder also by the name P as well. If mu is a binary operation in the preorder, we use the following notation. Give me any element A of P, mus of A is going to mean multiplication on the left by A. So mu has two arguments, we fix the left argument to A, and that gives us a unary operation. Similarly, superscript A is going to denote multiplication on the right by the fixed element A of the preorder. The last point is a reminder. If you have L and R being monotonic functions on the preorder, we say that L, R form an adjoint pair, or what is synonymous, they are a Galois connection, if for any two objects of the preorder B and C, L applied to B is less than or equal to C, if and only if B is less than or equal R applied to C. You can see the symmetry between L and R in this expression. What is that we are introducing? We want to solve expressions ax less than or equal to b. This requires us to have a preorder and a binary operation represented by dot. The main result is that this largest solution is given by some unary operation applied to b, that multiply with a, and unary operation of the result for some given unary operation. The ingredients we need in the theory, therefore, at least are a preorder, a binary operation, and a unary operation. And this is the algebraic structure we are introducing. We call it a preorder heap. A preorder heap has three objects. It has a preorder P, it has a binary operation mu by the name source multiplication, and it has a unary operation gamma, which is antitone, and this is called involution. The operations satisfy the following identities. Axiom 1. If you apply gamma twice, you get the identity. Axiom A2A. This is called left admissibility. If you give me any object A of the preorder, this identity has to hold. Mu sub A composed with gamma composed with mu superscript A composed with gamma is less than or equal to the identity. And the last requirement is analogous to the previous one. This is called right admissibility, and we simply flip the subindices and the superindices. We do not assume in this definition that mu is commutative. We do not even assume that it is associative. But in many theories, mu happens to be a commutative operation. When mu is commutative, the two admissibility conditions reduce to mu sub A composed with gamma squared is less than or equal to the identity. We'd like to discuss why these names that we have chosen. The name source multiplication comes from the following fact. As we will see soon, there is another fundamental binary operation in preordered heaps. In order to distinguish between the two, we needed to have an adjective. As we will see soon as well, mu happens to have a right adjoint. Therefore, whenever you apply mu to an object of the preorder, you obtain the source of the arrows involved in the adjunction. This is the reason we have a name source. The name involution is borrowed straight from sister algebras. In sister algebras, an involution is a unary operation which is its own inverse. And this is exactly the role that our gamma is playing here. This addresses the names. Let's focus on these admissibility conditions. Here we are just restating left admissibility. Mu sub A composed gamma composed mu superscript A composed gamma less than identity for some A given than P. In fact, for every A in P. Very good. Let's apply that expression to an object B of the preorder. If we apply that to B, we simply get the two sides applied to the same object, and so on. Now we are going to focus on the left-hand side of that expression. Let's take the last three functions and apply it to B, and let's give that a name. We are going to call that R. So R is equal to gamma composed with mu superscript A composed gamma, and that applied to B. What left admissibility means is that if you multiply A times R, that is less than or equal to B. Analogously, if we set L equal to gamma composed with mu sub A composed with gamma and apply that to B, what right admissibility means is that if you multiply L on the right with A, the result is less than or equal to B. What is surprising is the following. The admissibility conditions require that R is an admissible solution to AX less than or equal to B, and that L is an admissible solution to X times A less than or equal to B. What we will see is that these are sufficient conditions for them to be the largest solutions to those expressions. So from preorder heaps, we are saving ourselves the effort of carrying out an optimality argument for those. Let's look at an example. Let B be a Boolean lattice, and suppose that A, B are elements of our Boolean lattice. Source multiplication is the meat. So A and B. Involution is complementation. If you take two complements, you get the same thing. And if you have A less than or equal to B and you apply complements, you flip them. So it is antitone. We can check the admissibility conditions and we verify that they hold. So we conclude that a Boolean lattice is a preorder heap. Now we consider the notion of target multiplication. This is a binary operation derived from mu and gamma. It looks as follows. Tau is equal to, take mu, applied to two gammas, and we apply gamma to the result of that, as given in the expression there. And due to the fact that gamma square is the identity, we can flip the position of mu and tau in the expression, which means that mu and tau are related by a sort of generalization of De Morgan's identity. As we will see soon, target multiplication is a fundamental operation in preorder heaps. We already know that a Boolean lattice is a preorder heap. Will you show that? What is target multiplication for a Boolean lattice? It is simply disjunction. And now we are going to delve into the main result of our paper. The main result is this. If you give me a preorder heap P, for any element A of the preorder heap, mu sub A, comma, tau to the gamma A is a Galois connection. And also a Galois connection is the pair obtained by flipping the indices, subindices, and superindices. Let's focus on the first pair that we claim is a Galois connection. What does that mean? The fact that this is a Galois connection means that if you give me A, B, and X in the preorder heap, we have A times X is less than or equal to B if and only if X is less than or equal tau of B, comma, gamma A. In other words, this means that tau of B, comma, gamma A is the largest solution to the inequality, which is the problem we wanted to solve from the beginning. If we apply this notion to the Boolean lattice, which we show is a preorder heap, we can consider equations of the form A times X less than or equal to B, and the quotient by this theorem is given by tau to the gamma A of B, and that is B or not A, which is the same thing as A implies B. So with this theorem, we know how to find quotients for inequalities. Let's look at another example. There is a theory by the name assumed guarantee contracts that looks as follows. Let's fix a set V of behaviors. An assumed guarantee contract is a pair A, G of subsets of V that obey that expression. A union G is equal to V. Assumed guarantee contracts have a notion of a partial order. This is called refinement, and it is given by that expression. And we can set our preorder to that partial order. We can set source multiplication to contract composition. Contract composition is given by this expression. This operation is monotonic in both arguments. We can set involution to be a flipping of A and G in the pair. So AG becomes G, A. And this is easily seen to be antitone and satisfies gamma square equals the identity. Now we need to verify the admissibility conditions, and we can indeed show that the admissibility conditions hold. Our conclusion is that assumed guarantee contracts form a preorder heap. Target multiplication for assumed guarantee contracts we can compute to be this expression. It turns out that this expression matches an operation by the name merging that was introduced recently in the theory of assumed guarantee contracts. Also, from our theorem, we immediately get the quotient for an expression of the form C prime times X less than or equal to C. And we can compute this to be this expression, and this was also found in the last couple of years in its explicit form. It was our work, in fact, on assumed guarantee contracts that allow us to generalize many of the notions we saw there and realize that they were instances of a more general algebraic structure. Preorder heaps, we know what they are. What we are going to consider now is whether we can have maps between various preorder heaps. And this is something that will allow us to build a category of preorder heaps. So first, let's look at a map between preorder heaps. Let P and P prime be two preorder heaps. A preorder heap homomorphism is a function between P and P prime, which is monotonic, and which respects the multiplication and the involution of the two preorder heaps. In other words, it commutes with the multiplication and the involution. And now that we have maps between preorder heaps, we can define a category of preorder heaps to be defined as a class of preorder heaps together with arrows being given by preorder heap maps. This is a category that we have at our disposal now. We now introduce another algebraic definition by the name seed heaps. Seed heaps are going to be useful when we have objects defined on multiple domains. For instance, you have one domain that defines a certain class of objects, another domain that defines another class of objects, and we wish to combine them somehow. Like in this example, suppose that L1 is a language over the alphabet sigma 1, and L2 is a language over sigma 2. We can set a preorder heap to be the language over the given alphabet. We know this is a Boolean lattice, therefore we know it is a preorder heap. The question is, L1 and L2 are living in different worlds, are defined in different domains. How do we define an operation that allows us to merge these two objects? Here's a solution. Find a bigger alphabet, sigma 3, and ship L1 and L2 to the preorder heap given by that bigger alphabet. Because that is a preorder heap, it has a notion of multiplication. Therefore, we can just multiply locally in that preorder heap piece of sigma 3. What we notice immediately is that sigma 3 only depends on sigma 1 and sigma 2. So we can write sigma 3 equals to sigma 1 times sigma 2 for some binary operation dot. The dependence of this operation looks as follows. It is commutative because it shouldn't matter whether we multiply sigma 2 by sigma 1 or the opposite. We should obtain the same result. By the same reasoning, it should be associative. If we have three alphabets that we are joining, it shouldn't matter how we place the parentheses in the operation. And finally, if you have two languages defined over the same domain, in order to operate on those two languages, you should not need to go to another alphabet in order to define the operation. You have everything you need. So it should be idempotent. So now we are saying that the sigmas are coming from an algebraic structure that has a binary operation with its properties. It means that the sigma i's are drawn from a semi-lattice. That is exactly the definition of a semi-lattice. The elements of the semi-lattice are indexing our preordered heaps. So every sigma I goes to a preordered heap of its own. For every x and y such that x is less than y in the semi-lattice, there is a map from the preorder heap indexed by x to the preorder heap indexed by y. And this is a map that allows us to ship languages from px to py. These maps should make the following diagram commute. The diagram says the following. Suppose that you have a language in px and you want to ship that language into pz. It shouldn't matter whether you first go to pc directly from px or whether you first go to py and then you go to pz. We should get the same result. These considerations tell us that what we have is a functor from the category of the semi-lattice S to the preorder heap category. The functor f gives us a preorder heap for every x. For convenience of notation, we are going to say px is the preorder heap given by f applied to the element x of the semi-lattice. And we use the same subindices for all the operations defined in the preorder heap. The only arrows that exist in the category S are whenever x is less than or equal to y. It means that our functor is mapping those arrows in the semi-lattice to preorder heap maps. And there is only one of them because there is at most one of them between any two objects of the semi-lattice. These maps iota are called concretizations. And here we follow the notation of abstract interpretation, because we understand that when we go to a preorder heap with a bigger alphabet, we have more detail available to us. This is why we call it concretization. This allows us to introduce the notion of a seed heap. Let S be a semi-lattice, an upper semi-lattice, and let F be a functor from the category S to the category of preorder heaps. A seed heap consists of the following. It has a set P, which is the direct sum of all the preorder heap sets indexed by the objects of the semi-lattice. It also has a less than or equal, defined as follows. The less than or equal is a relation that works like this. If you give me any two objects in the semi-lattice, and you give me an object A belonging to the preorder heap indexed by object X, an element B belonging to the preorder heap indexed by element Y, we say that A is less than or equal to B if there is an element Z in the semi-lattice such that when we ship A to P sub Z and when we ship B to P sub Z, we get a less than or equal defined in the preorder heap PZ. If that happens, then we say that A is less than or equal to B. Seed heaps have a binary operation called source multiplication, and it works as follows. If you give me xy in the semi-lattice, the multiplication is defined as follows. You go from px to p sub xy. You go from py to p sub xy. In fact, we are shipping our objects from px and py to the common domain p sub xy, and that is a preorder heap. So we have a well-defined notion of multiplication there. Because we have a well-known notion of multiplication, we can define our global multiplication mu, the red arrow, to be exactly that. I want to mention that in order to define this binary multiplication mu, we are introducing this entire structure. This is the operation that is merging objects of different domains. The final object that we have in the definition of a seed heap is involution, and involution is given by whenever you apply gamma to an object A of the seed heap, that is the same thing as applying the local gamma to that object. Target multiplication is defined exactly as you would expect. Instead of having mu in the previous diagram, we have tau in the diagram, and we obtain the definition of tau. Why are seed heaps interesting? Well, they are interesting because the relation less than equal that we introduce is a preorder. Source multiplication on P is monotonic in both arguments. A seed heap happens to be a preorder heap, which means that we know how to solve equations over seed heaps as well. The solution to A times X less than or equal to B is given by our previous theorem, tau to the gamma A of B. Now we look at an example. Let's consider the asynchronous product. L1, L2 are languages over, respectively, sigma 1 and sigma 2. They are disjoint. The asynchronous product gives take all the words of L1 and L2 and do all possible interleavings between them. Example, suppose that language L1 is AB. Language L2 is the string CD over the given alphabets. If we take the asynchronous product, we interleave them in all ways while respecting the order of the string. How do we build a seed heap out of this? We can set the semi-lattice to contain a collection of alphabets. The semi-lattice operation is going to be set union. If you have alphabet I, alphabet J, you multiply them, means you take union between them. The preorder heaps are the languages defined over the given alphabets. The preorder heap maps are given by the following operation. You take a language defined over a preorder heap, and whenever you go to the union of the two alphabets, you extend all the words of your language to the interleavings of that word with all possible words generated from the symbols not in the local alphabet. This is the expression, the operation denoted by that formula. we can show that this gives us a zipped heap, which means that we know how to find expressions a times x less than or equal to b for the asynchronous product. What is the main takeaway? Many existing compositional theories are preordered heaps, Boolean lattices, assumed guarantee contracts, interface automata, languages over synchronous and asynchronous composition. We show this in our paper. If you have a theory with preorders in which you want to solve inequalities of the form ax less than or equal to b, check whether your theory is a preordered heap. And if it is, the theory of preordered heaps immediately gives you a quotient. I am very grateful for your attention. I hope you have a good day.